you जगदीश सर इनको छोड़
ಇದು ಬೇಕಲ್ಲ, ಡೋರ್ ಓಪನ್ ಮಾಡಲ್ಲ ಅವ್ರು ಇನ್ನ. ಬ್ರೋ ಇಲ್ಲಿಂದ ಬೇಕಾ ಒಳಗಡೆಯಿಂದ ಬೇಕು? ಇಲ್ಲಿಂದ ಬೇಕಾ ಒಳಗಡೆಯಿಂದ ಬೇಕು? ಜಾಗ
Detailing when you make it up all the levels of height, all these chairs are aligned, everything to that. That is my sister Neela, she is also one of the directors of the kitchen. And my younger daughter Sangeeta is one of so I think when you start getting smart is it?
Sir, is that chair okay? Yes.
That's
You're gonna have to move.
ಲೈವ್ ಕೆಲಸ ಮಾಡ್ತೀನಿ. ಅದೆಲ್ಲ ಹೋದ್ಮೇಲೆ ಟ್ರೈಪಾಡ್ ಇಡಬೇಕು. ನಾನು ಕಟ್ ಮಾಡು ಅಂತ ಹೇಳಕ್ಕೆ ಬೇಡ, ಬಿಡಿ ಇಟ್ಕೊಂಡಿರಿ ನೀನೆ. ಇಲ್ಲ ಆಗ್ತಿದೆ, ಲೈವ್ ಹೋಗ್ತಿರುತ್ತೆ ಅಂದರೆ ಅವ್ರು ಕೊಟ್ಟಿದ್ದಾರೆಲ್ಲ ಗೊತ್ತಿಲ್ಲ ನನಗೆ. ಕೇಳಿ, ಲೈವ್ ಕೊಟ್ಬಿಡ ಕೇಳಿ. ಇದೆಲ್ಲ ಬೇಕಾಗ ಇದೆಲ್ಲ ಮಾಡ್ದಂಗೆ ಎಲ್ಲ 360 ಕ್ಯಾಮ್ರಾ ಹಾಕಿ ಆ ಥರ ಸ್ಟಾಪ್ ಮೋಷನ್ ಥರ ತೆಗೆದ್ರೆ ಹಾಂ. ಟ್ರೆಡಿಷನಲ್ ಕ್ಲೀನ್ ಕಟ್ ಪೆನ್ಸಿಲ್
ಈ ಲೈವ್ ಇಟ್ಟಿದ್ರೆ ಅವ್ರು ರೆಕಾರ್ಡ್ ಮಾಡ್ಕೊಬೋದಾ? ಬರೀ ಹಿಂಗೆ ನಾವು ರೆಕಾರ್ಡ್ ಮಾಡೋದಿಲ್ಲ, ಮಾಡ್ಕೊಬೋದು ಅದ್ರಲ್ಲಿ. ಹಂಗೆ
ನಾನು ಮಾಡ್ತಾನಿಲ್ಲ, ನಂಗೆ ಗೊತ್ತಿಲ್ಲ.
ಮಾಡ್ತಾವ, ರೆಕಾರ್ಡಿಂಗ್ ಇದೆ
ಮಾಡ್ಬೋದು. ಮೇಲೆ ಇಟ್ಬಿಡ್ತೀನಿ. ಹೋಗ್ತಾನೆ ಅಂತ ಏನೋ ಮಾತಾಡಬಾರ್ದು ರೆಕಾರ್ಡಿಂಗ್ ಆಫ್ ಮಾಡೋಕ್ಕೆ ವಾಯ್ಸ್ ಲೈವ್ ವಾಯ್ಸ್ ಆಫ್ ಮಾಡೋಕ್ಕೆ
Good afternoon, everyone. I would like to welcome our eminent guests, colleagues, friends, the IISC fraternity to the inauguration of the SP Narasaiah Auditorium and the inaugural memorial lecture. I would first like to invite Professor Rangarajan, Professor Kulkarni, Professor Ashokan, Mr. Nagarjun, and Mr. Prashant to light the lamp. I now request Professor Ashokan to give the welcome address.
Good afternoon, everyone. I welcome you all for this very important event in the history of the Department of Instrumentation and Applied Physics, which is the inauguration of Sri S.P. Narasaiah Auditorium. In a way, more than 6 decades of relationship between Mr. Narasaiah and also HHP with the Institute and IAP is going to be written in stone today in the form of this auditorium. So you will be hearing more about the association of Sri Narasaiah, who is fondly known as SVL, with the Institute and also with our department from Mr. Prashant, the Managing Director of HHP, a little later on. And it's my pleasant duty today to propose the welcome address. It is with immense gratitude I welcome Srimati Sarojini Devi, wife of Sri Narasaiah, late Sri Narasaiah, and other members of the family for this inaugural function. I also welcome Professor Rangarajan, Director of IAAC, who has been highly instrumental in making this auditorium a reality. He was involved right from the day one, first as the chair of Office of Alumni Affairs and Development. I think the seeds of the auditorium was sown on the day when we we went together, and then we went to the director at the time and then proposed the auditorium construction and so on. So he has been a consistent support and encouragement for all of us to bring this auditorium into existence. So I warmly welcome Professor Kulkarni, President of Jawaharlal Nehru Center for Advanced Scientific Research, who will be delivering the first SVN Memorial Lecture today. Thanks to HHV, this lecture will be a very regular event of our division in the years to come. So I am very thankful to them for this kind gesture. I also welcome Professor Kaushal Verma, the Dean, Physical and Mathematical Sciences Division, our Registrar of Indian Institute of Science, Professor Fanindra, the Chair of Office of Alumni Affairs and Development, Professor Narahari, and former Dean, and other faculty members and chairs of the department who have been supportive of our department at every stage and who have graced the occasion today. I am also delighted to welcome the distinguished guests from other institutions, administrative officers of IAC, chairs of various departments for their kind presence. I fondly welcome Professor M.V. Krishnamurthy and Professor Rajanna, the former chairs of our department, who have been, associated with the department for a very, very long time, and who are physically present here today. And also, Professor Mohan will be joining us online through the video streaming. He will also be there attending this event. So I finally welcome all the faculty members, staff and students of the department, faculty members from other departments who are present here for this August function. So I welcome one and all. And before I step down, I would like to give a couple of minutes about the genesis of this auditorium. So a few years back, Professor Balram called me one day and he said, SVN Garu has mentioned to Professor Ram Sharma about the possibility of starting something or establishing a facility at our department. Then he said, can you go and meet? Then myself and Professor Mohan Rao went to HHV, met him, and then before that we had a small discussion what we could ask. And let me tell you, he said, Babu, what do you want? See, he only told what we wanted. He never discussed anything further. He said, take it. Whatever we asked, he said, take it. So there is no discussion, there is nothing. So we could have asked more, he could have given more. And only thing he said, Babu, will it be ready before I leave? So we said yes, very strongly, but unfortunately we couldn't fulfill this promise. And but all is well that ends well. I think his soul will be here to bless us on this occasion and also bless the department in the years to come. Thank you very much.
Thank you, Professor Ashokan. I now request Mr. Prashant Sakamuri, Managing Director in Hindhai Vacuum, to introduce the gathering to Mr. Narasaiah's story and the reason we are here today.
Good afternoon, everyone, and chief guest for this eminent function, Director, Professor of IISc, Professor Rajan, and Professor Kulkarni, esteemed members of all the IISc over the years, probably people who have been part of this whole building, this whole institution over the years, a lot of them, whom I'm seeing them right down from probably a lot of them are from their early, some of them as old as into their late 80s who are here today. All the members of the scientific and industrial community who are here. Ladies and gentlemen, welcome again. And it is my privilege today and my pleasure to introduce the man of the evening, Mr. Narasaiah, to each one of you. So, SVN, as he's very fondly called, was born in Thaduai on September 28, 1924. It is still a part of the Guntur district in Andhra Pradesh. And from there, he had his initial education at Challapalli in the Krishna district of Andhra Pradesh. It was in Challapalli that he was exposed to various political struggles of that time and the freedom movements. He was seeing and hearing Gandhi during his regular visits to Andhra Pradesh and Vijayawada for various of his trips in public meetings. He watched the growth of the Communist Party of Andhra Pradesh at that point of time, faced the challenges of being under British rule. And this set a stage for him to become an active member of the student movement in those days and the freedom struggle. So, later on, as he went on to his higher education period, he became an active member of the Communist Party of India, which fought the oppression of that time of the Razakars, especially of the peasants of Telangana. He was involved in also building a whole younger cadre base through his student federation during his college days. He married Sarojini Devi, an activist like him, who is also here with us today. So, thank you for being with us. Later on from there, he started his career as a photojournalist post the World War II and later became an editor of a newspaper in Vijayawada. He moved to Hyderabad to make audiovisual educational movies. These were basically focused on science and technology and all this being behind the camera and his travels in Eastern Europe around that post the Second World War inscribed in him an urge to manufacture camera lenses in India. So that was basically the whole idea behind which initially HHV started. It was in 1964 when he was discussing with a few friends, including Professor Ramakrishna Rao, who was then an active member of CSIL out here at the Indian Institute of Science, because this department used to be the Central Instruments and Services Laboratory. It was before it became an independent department. So they all basically invited him to move to Bangalore to seek an opportunity to chase his passion and build a business around science and optics. So that was what was basically brought him in here. So in 60s, actually, at that point of time, Bangalore was considered the new age science capital of India. It was the knowledge centers like IISc, the HMT, BHEL, BELs, all the public sectors and various other defense research organizations like HAL. They were becoming the fulcrum for manufacturing scientific and precision equipment in the country. So that with these kind of establishments, this was the city which was attracting the cream of talent from across corners of the country, and it became the center to build the core engineering base for the country at that point of time. So manufacturing establishing small-scale industries was basically a main focus of independent India, which is there. And this is an India at that point of time which we should also try to picture was struggling to break free of various challenges of poverty, lack of education, basic infrastructure, and extremely low on foreign exchange. It was here in ISC and CISL, which is now the Department of Instrumentation and Applied Physics, that SVN met Professor Howell. Professor Howell was a visiting scientist from the UK, and he expressed a desire with him that he would like to make optical zoom lenses. And that was when HHV was formed with an initial objective of making and producing zoom lenses. But to build that, they needed equipment. They needed equipment which to do some coatings and various kinds of filters which were involved. So that was when they said, let us build our own equipment for that, because we cannot afford to import equipment at that point of time. So precision engineering and manufacturing at that time were very nascent, and with the available engineering standards and low infrastructure, they realized that making an optical element, especially a zoom lens, is and especially with an undercapitalized small-scale industry like HHV at that time, would have no chance of survival. So that was where basically the kind of the visionary in SVN came into him, and where he said, let me not go further onto this process where I would probably end up with nothing and we would not be able to achieve our ends, but let me find a way in which we would start finding a purpose in what we have started to do. And there they saw a need, a purpose, and an opportunity, and that was basically building vacuum equipment, and that was the start of building a business out there. So he was entering a field where he had no domain knowledge. He was not an engineer, he was not a scientist. So he had to self-educate and surround himself with experts. He integrated himself with almost every knowledge center of that time and built associations with almost all the leading research and learning centers of that time. He had close interactions with his mentors and friends, well-wishers. Professor Dhawan was one of them, and he was always one who actually guided him right through many of his challenges across the life and span of HHV. Some of the leading scientists of that time, like Professor Suryan Vasudev Murthy from the ISC, Professor Kalam and Professor Rao from the Space Department, and many more from Atomic Energy or DRDO, they all came out to help him to develop a long-term vision to foresee the requirements of the whole spectrum of vacuum ecosystem. At that point of time, slowly there was also the country was going through an embargo, which was instituted basically because of our nuclear policy of that time. And with that embargo, there was no free flow of vacuum equipment, which was considered strategic. And for that reason, it was basically HHV became a core to many scientific institutions to help build infrastructure at that point of time. So the support and the requirements which were asked for were basically where Mr. Narasaiah always stepped forward to see that and saying that we will build. In fact, there were times when even attempted to start building an electron microscope in the early 80s. And Mr. Srishail is here in this audience today, and he was one of the people who started the whole project with him. In fact, the country was going through various challenges, and in fact, it had also tried to start a vacuum business. Government of India started a vacuum business with Indo-Burma Petroleum at that time, but it just could not suffice to meet the requirement of the country. So Narasaiah's SVN strength was basically his relationship building with people. He was a tall and towering personality, was an active member of industries associations, and his biggest strength was he was a uncompromising person when it came to high ethical values. He was not easily swayed by any easy money that came from, at that point, the licensing system or the quota practices, which were basically very popular with the small-scale industrialists who could benefit significantly and sell quotas at that time. He clearly understood that there was a lack of human resource and skill in the field, established a strong development program in HHV, which included at that time a training center and an active skill development program with a foreman research training in Karnataka and Bangalore out there. This was very rare for a small-scale industry to take up these steps, but with his limited resources, he was able to always be there to try out new ideas and new thoughts and challenges. So he was always the first to accept any challenge, whether it was basically to set up a powder degassing facility for somebody, or to establish metal separation, or take up a multi-axis robotic sputter coater for coating stealth coatings on the aircraft canopies. So he was always front end of any team which took up these kind of activities. In fact, he was also a person who shared success with all the members of his team and took total responsibility for anything which failed. Even as he moved on in age, he was always kept up to date with what was happening in the organization. Even in as late as 94, 95, he would be involved in board meetings to understand what was going on and ensuring that no core values of his organization were ever compromised. Even till his last days, he was actively involved in board meetings. He was recognized for his efforts by various industry organizations and scientific bodies like the Indian Vacuum Society, the Indian Institute of Metals, the Rotary, the Government of Karnataka, and the company have also achieved many laurels under his guidance, including the President's Medal for Technology Development. So he was never one for profit. Profit was not in our company, profit was a bad word coming in from a leftist background. It was a bad word till probably me and my brother joined the company. So he always would say, if I have a positive cash flow, I know that there is a profit somewhere, and the rest I leave it to the accountants. My job is to provide a holistic umbrella for all the people in my organization and see that I meet my customers' expectations. So one of his close associations was always with Professor Dhawan, who was his mentor, friend and guide. So he would come in regularly to the ISC. Every Sunday, more or less, he would be here for a regular periodic meeting with Professor Dhawan, and drew a lot of inspiration subsequent to when Professor Dhawan even retired from the Space Department and was saying they would still continue to meet regularly, and they would continue to discuss thoughts and vision as to what they would have to do to make a difference to helping infrastructure in Indian science. Almost all the thoughts and initial work which were there at that point of time started out from this very department. So that is where we also all felt that it's only true and fitting that he be a part of the space that would propagate and further the scientific thought of the community that helped establish and build the first and leading vacuum technology company in India from here. The hope is this auditorium fosters many discussions and focuses on science and technology that will be the starting point for more and more organizations like HHV. Thank you very much. And just to let you know that Mr. Narasaiah passed away on 8th of October 2021 at a ripe age of 97 years. Thank you very much.
Thank you, Mr. Prashant. I now request our chief guests, Professor Rangarajan and Professor Kulkarni, to please take a seat at the dais. I now request Professor Rangarajan to please address the gathering.
Thank you. It's an honor for me to be part of this inauguration. As Ashokan said, I was there from the beginning, and it is really. I wish we could have done it, about a year ago, but still that was not to be. But at least we have done it now. I see it has come out very well. I thank both of the entire family. And I should thank the entire family for making this happen. And
ensuring that we have a very quality space for the department to have all its gathering. This will serve as a nodal point for the department for all its meetings. And I'm sure once people see this auditorium, I'm sure there'll be a lot of people from other departments who want to use this auditorium on an ongoing basis. So this was very kind and generous of the family, and I'm very happy that all of you could be here and be part of this event. Thank you very much.
Thank you, Professor Rangarajan. I now request Professor Phanindra to please address the audience.
It's an honor for me to address the gathering. It came as a surprise for me, but nevertheless, I would like to thank the family for donating this and as well as contributing towards the operations of making this operational. And again, I would like to state that very few people come forward and remember the institute for what it has done. Even though we have been a focal point for a long time. And it is nice of HHV that it has thought about us and then have instituted this space, especially to propagate the scientific thought. And that is very important, and it's going to be playing a crucial role. Again, I would like to thank all of them. I would like to, even though I'm representing the Office of Development, which oversees all the donations that come to IAC, I think this is very dear to me because I was an alumnus of here. And I'm very glad to see Professor Krishnamurthy here, who was the chairman when I was a student. So again, I would like to thank everybody for joining here. Thank you very much.
Thank you, Professor Phanindra. We would now like to present mementos to some of the guests. So I would request Professor Rangarajan and Kulkarni to stay on the stage, but we're just going to have to move the table back. I also request Professor Ashokan, Professor Kaushal Verma.
It's fine.
And Professor Phanindra to please.
So late.
I request Ms. Leela Amarmeni to please present the bouquet and memento to Dr. Rangarajan. I request Ms. Geeta Sakamuri to please present the bouquet and memento to Dr. Kulkarni. I now request Ms. Padmaja Sakamuri to please present the bouquet and memento to Dr. Ashokan. I also request Professor Chandni to please present the bouquet and memento to Professor Puneet. Just take a picture with all of them. We'd like to thank everyone. This is the completion of the inauguration. We'll be taking a 5-minute break, and after that we'll be starting with the inaugural memorial lecture. Thank you.
No, please.
by the Karnataka State Council for Science and Technology. Professor C.N.R. Rao National Prize for Chemical Research 2020 by Chemical Research Society of India. Honorable Fellowship of Karnataka Science and Technology Academy in the year 2020. Kannada Rajyotsava Award 2021. B.M. Birla Science Prize in Chemistry in 2002. Chemical Research Society of India Lecture Medal 2003, and Professor C.N.R. Rao Oration Award in the year 2006. He has over 300 journal publications and 26 patents, and has mentored a number of masters and PhD work and continues to do so. His research interests are focused on new strategies in synthesis of nanomaterials, nanopatterning and nano-device fabrication, including molecular systems. And his recipes emphasize the importance of simple design, near ambient working conditions, solution-based processing, as well as low-cost instrumentation. And his group strives to translate nano research findings into affordable technology. HHV's and professors' research interests crossed path in the year 2016 when both groups realized that we had synergistic technologies that could be combined to offer a unique product proposition. So at that time, HHV had developed the machinery and the associated process technology for fabrication of large area transparent conductive oxides. And the professor's research group had done extensive developments in the area of crackle lithography. And this is used to produce fine metal meshes. So both the groups started working together, and we have been working together since. So in a nutshell, Professor G.U. Kulkarni is an eminent scientist, technologist, and science administrator. On a personal note, he is a lover of good food and enjoys eating as well as treating others around him to good food. So now I request him to treat us all to a sumptuous lecture.
I would now like to welcome and invite Professor Kulkarni to please deliver the first SV Narasaiah Memorial Lecture.
Good afternoon, good evening. It's a pleasure to be part of this event, inauguration of the SVN Auditorium. Thank you, Mr. Prashant, for inviting me. Thank you, Professor Ashokan, for having me here, and also other dignitaries, HHV family, faculty colleagues, staff, students. Pleasure to be with you all. I used to live next door. I did my PhD at solid-state and structural chemistry unit, and this department isn't anything unfamiliar to me. Every alternate day I used to be around here using their machine shop and talking to people, doing things. So it's again pleasure to be back in the department. With the addition that this is a new site to me, and it's very nicely done. Congratulations to HHV and also to IAC Installation Department having come up with this auditorium. And it's an absolute honor to give this inaugural SV Narasaiah Memorial Lecture. I had the honor and opportunity to meet Mr. Narasaiah in the Pune establishment of HHV a couple of years ago. Though I had heard of him a lot, even during my student days, even Professor C.N. Narasaiah used to mention about him. This is one individual whom you can approach for instrumentation. My PhD was partly to do with instrumentation, so I heard him mention Mr. Narasaiah's name. And I had the opportunity a couple of years ago in the Pune laboratory. And I have seen even the Navas-Pate and all the entire establishment of HHV. I'm quite familiar with their expansion, the way they do the reach out to various research labs and across India, even abroad, and have it, it's a very well known amongst all of us. So with these words, I would like to begin my lecture. I have kept the title bit general, that is to do with glass. Okay. Before I really get into it, we're all academic people, so we'd like to do our bit of marketing in what all we do. I work in few verticals as I've shown here. One is to do with growing metal nanoparticles, nanocrystals in varied lattices. So we actually make gold. The gold I'm wearing here, the ring, this is in a crystal structure called face-centered cubic structure. Most of us are familiar with that. And in my laboratory, we grow gold into something very different, which is even nobler than this gold. I had an interview by the journal, the magazine New Scientist a couple of years ago, how we make it, is it of commercial interest and whatnot. Even with the HHU team also we had a dialogue on it. We are unable to actually come up with huge throughput of this, but for the laboratory purpose, we can actually make crystallized gold into a different lattice, and that can even stand mercury in terms of forming amalgam. It's very different, strange properties of gold expressed in these microcrystals. And I must thank Prashant here for the picture what is shown there on the this side. For the face mask what we made. We were struggling in our lab during COVID times, lockdown time, we were struggling, and Prashant came around and said, why don't you commercialize that? So he actually connected us with another industry wherein we took his help and commercialized. It's available now in all the online markets and all that. Besides that, in the last 2-3 years, we have jumped into new areas now, using metal nanostructures, trying to make neuromorphic devices. We already have very positive results. Students around here, anyone feels interested, could visit our lab and we can exchange and discussion. So now I'll get to the core topic. I'll keep my talk rather semi-technical, given the composition of the audience here, and I need not cover everything what I have brought in here, given the time limitation and all that. I just want to carry across a message, how much more is required to be done with a conventional material like glass. When I say glass, I mean highly non-technical, the glass of what we use in making window panes and all that. So I'm going to address that issue through my talk. So here is the examples here where all we use glass. I don't have to get into any of these details. What I want to emphasize is that the usage of glass has gone many-fold in the last decade or so. Nowadays you have high-rise buildings which are entirely covered by glass panes, right? And you think of the application, you have either plastic or glass there as a component at least. So there is increasing usage of glass, but glass has more or less remained the same over hundreds of years. Very little development, very little technological changes one could see in the history of glass making. People learned long ago, bringing in, in the molten glass, in glass making, if we shove in a bit of gold or silver and tiny particles of bronze and all the oxides, glass can be made into certain color. And that should be predetermined based on the base material what we tend to use. And once colored, it can hardly be changed. It is not switchable. It just to be called as colored glass, and it is applicable only in certain specific applications like this. Can we turn off this slide? My slides are looking a little duller than what I would rather wish to have. Yeah, I think this is definitely better. So I have shown there what kind of elements or compounds can be added to achieve different colorations and all. And even during student days, I used to work on these sort of compounds to modify for various other purposes. And glass per se, though there have been lots of development in terms of tuning the thermal properties, optical properties, mechanical properties, there is hardly anything being done with respect to electrical. It's extremely challenging. I'll come to that in a minute or so. So I'll be addressing some of those issues in my talk now. But otherwise, playing around with the surface of glass, like having a laminated glass with various types of coatings and all, they're all quite prevalent. Of late, with the advent of nanotechnology, people learned how to coat glass with almost a single monolayer or atomically thin layers and modify the properties of glass. Obviously I can't be bringing in all sorts of examples from the literature. Just to showcase one or two examples, here is a glass which can remain unfogged. You can see anti-fogging in action here. So even under high humidity condition, you can maintain a piece of glass without fogging. You can readily see applications because you want to have it as a windshield for automobile and whatnot. And the surface of glass can be converted to antimicrobial type of property by bringing in certain metal elements there, which could actually rather kill individual viruses and bacteria species, which could be rather hosted on a typical glass surface. So these all have gained importance, particularly during the pandemic time, and people have come up with lots of formulations, and some of them are commercially available too. You can take the sprays and all available, you can spray, and some of those sprays and all contain such formulations where they could be bioactive in removing the pathogens. And so this way, with the developments in nanoscience and technology, people have learned how to modify glass surfaces. What I'm going to address is one particular issue with respect to glass, that is, how do we make it more and more functional, particularly in the context of electronic devices. We are really working between electrical and optical properties, what we call as optoelectronic properties. So here is an example. These large panes are made of glass. They can get converted to being translucent or transparent. You readily see the advantage, right? So even in this kind of a hall, if we can have these windows covered with glass panes, wherein they become switchable. So at times you just like to have glass switched over to transparent state, wherein you'll be able to see the greenery outside, if at all it is green outside. I don't know what is there. So it gives you the option of opening up your arena, your room or space, whatever, to the outside world whenever you wish, only if you can exercise this particular control. This is also of importance in terms of thermal management. If we have an auditorium like this, and this is now air conditioned, imagine that it's truly a sunny day outside, and you want to block certain radiation, like IR radiation, entering the room in order to contain and manage the thermal aspects. So we spend a lot of energy in terms of how to air condition the rooms, and in that context also having a functional aspect to glass, whether you want to have glass completely transparent or translucent, opaque, or colored in whatever fashion we want to. So those concepts actually are extremely important for energy management. People nowadays talk about zero energy buildings, popular technology. That is like, this building doesn't use any external power. Can we run and maintain everything with whatever power like solar and whatnot generated internally to the extent possible. So that is the target, aim to achieve, and even architecturally people are moving towards that. In that context, also having a smart glass with the desired optoelectronic properties would be of utmost importance. So in terms of smart windows, as I showed the example there are a couple of technologies already out in the market. Thermochromic, suspended particle technology, and then polymer dispersed liquid crystal PDLC technology, and electrochromic. I'll just spend a few seconds with each just to emphasize the importance and the extent which they are trying to barge in, emerge in the market, in the world market. For example, this building, this is the real building. These are real photographs from Google Images. You can see this glass is now, the whole dome is colored now, and the coloration itself can vary depending on sunlight. It's not truly sunlight. Sun brings in the warmth, and with heating, it can change its color. This is a typically vanadium oxide kind of system, wherein because of the slight increase in temperature, it can get colored. And people have used such technologies as coatings to glass, and in the evening it becomes completely transparent, and that's what probably you desire. And so thermochromic is one market which is already there, but here you have hardly any control. It is switchable, but it depends on the warmth or the local temperature which is imparted. Then suspended particle windows. Here you have a set of particles, typically magnetic particles, and depending on they're also anisotropic. Depending on the magnetic field around or the electrical field around, they can actually be made to organize themselves in the little cavity, and they can control the light. This technology is also in use in a limited way. Then electrochromic smart windows, these are quite popular. If you have traveled in Dreamliner, you have these passenger windows which can be, glass can be made tinted. It can be made completely dark also. There's a little toggle switch here. If you go on pressing it and hold it for a few seconds, then you can go on changing the color. Alternatively, you can also push it to be completely transparent. And so here you can actually vividly realize the functionality aspect of glass. How glass is now. Our passenger windows used to be very passive, but in Dreamliner it is a functional glass now. And so how this is made is because of the electrochromic concept. And here you have two conducting glass panes. In between there is an active material, typically tungsten oxide based material. With the application of electricity, there is also lithium electrolyte around there, and it's intercalation, de-intercalation taking place, and that can bring about the color changes. That's all about the solid-state physics and chemistry. Those principles come into play. The point I'm trying to make is this is no longer a simple piece of glass. This is actually a device. It's actually, you can say, a laptop is fixed at each window. You can imagine now that big a plane and so many laptops or TV screens fixed there. It's as good as that. They're all electronic devices. They are not just simply glasses. How do we talk about the benchmarks here? There are several benchmarking parameters, but I've just brought in a couple of them. How good a window is, glass pane is, in terms of blocking IR and operation temperature, transmittance, haze. You can go on like the power requirement. That's also an important thing. And the switching speed. Is there a curtain effect like lift up and lift down, put down? And then the device calibration. There are so many. And as far as technology development concerned, and if you want to order in the market the kind of technology you desire, there are another dozen of them. Specs are very well defined. You can actually place an order for the product and the number of items what you want, and there are people who will supply. But nonetheless, this has not become extremely widespread because of the issue of affordability. There is a huge manufacturing cost and operating energy related issues there. I said, you think about it now that you have to spend a couple of watts per meter square to make the device functioning. So if you are giving each passenger one window, you can think all the 100 TVs are, not 100, more than that, I think maybe 300 or so TVs, you're turning on, turning off. There's also a concept of windowless plane. People have predicted that in probably 10, 20 years time, we'll have planes which will not have any windows at all. Because you can put some cameras outside and bring in the wires and you can make everything display at the will of the passenger, right? So you don't have to have necessarily a window, which is sort of you are all engineers, many of you are engineers, you can realize to build a window inside this, it's essentially a vacuum system plane inside. So given all that, there is a lot of importance given to redefine the glass itself, okay? And so parameters are available, specs are available, technology is available, but products are not being used because of the cost related issues. This is the topic I took upon head on and started addressing it in the group, and it is to do with the glass itself. Glass, as we know, it's extremely electrically insulating. It's a ceramic actually, aluminum silicate with a very wide band gap. It's an insulator. And all these devices like to have glass electrically conducting. Because when I take my cell phone and do something on the screen, you need to see activation. That's all electrical activation. And if glass is highly insulating, there is no way that I can get those functionalities into the electronics. So glass has to be made conducting. And it is not that there are no developments. Because the developments few decades ago in solid-state physics, solid-state chemistry, I learned it during my PhD time. And actually, as we finished our degrees and got into the profession, we could see whatever we were studying being translated to technology. This is one among them. This is the Indian tin oxide, the cheap tin, its oxide, SnO2, is doped with indium. Indium is like silver, is as expensive as silver, as abundant as silver, not so abundant. And that is taken and doped with tin. And what we realize in terms of solid-state physics is the tin pumps in some conducting electrons in the conduction band. Importantly, it leaves the band gap completely clear. So this is one God-given material where visible light can easily pass through without giving any coloration to the glass. At the same time, glass is made conducting because of this coating. And you can buy these glass pieces in the market. They look like this. And these are the very glasses which actually form the top screen of all the smartphones and many TVs, interactive TVs and all sorts of screens, whatever we come with, including ATM machines, everywhere. These are the glasses which are there on top. And there are lots of limitations. One biggest limitation is whatever coating we are doing is oxide, so it's a ceramic. So the moment you think of bending it, I can bring this coating on PET also, plastic. I cannot bend it because the ceramic will crack. The moment it cracks, you lose out the electrical properties. So there are technological challenges. That is the reason you still don't have a foldable TV or foldable phone. This is the biggest hurdle. And as you can see now, I don't have to tell you how much demand is there for this kind of coating because all of us are using big devices now and lots of devices. Each individual is using lots of devices. So the requirement of indium has gone up a lot. Tin is really there everywhere. There's no issue. It's inexpensive, it's environmentally friendly, everything is fine. The problem is with indium because it's not that easily available. We surveyed and we wrote a review article a couple of years ago and placed ITO here. You see, this is the process cost and the material cost. We are paying for our electronic devices. The most of the cost goes for, 1/3 of the cost goes for IT. And people didn't keep quiet in the last 2 decades, 3 decades. They have tried lots of other materials. What is desired is alternate, you need to have transparent conducting electrode, somewhere placed here, very low process cost and very low material cost. And this is something which we are addressing in the group. The idea came from somewhere else. Let me not get into too many details here. This example suffices to what I want to come to. You may have seen a dried lake bed. You tend to see these are all the mud and lots of cracks formed in between. The beauty about this particular dried lake is that the cracks are well formed, they're all interconnected, and we love them. We need such examples. Just that we don't use the ordinary mud, but in the lab we make nano mud, very, very fine particulate system in a given solvent. And when we disperse it as a thin film thickness could be of the order of only a few hundred nanometers, and that dries up producing fine cracks. These are the particles we use. These are readily available, inexpensive acrylic resin particles, and there are a lot of reasons why it behaves so and all that. I'll not get into that. This is the real experiment. You see the photograph of an area of 20 by 15 centimeter square, coating of this particular particle system, and the solvent is taken away, and the dried system is here. And wherever you put the optical microscope head, you can see lots of these cracks there. So the entire system is now having interconnected crack system, much the way what we saw with the lake bed. And you can calculate the fill factor of the cracks, that's around 15%. Why I'm talking so much about these cracks? Because these cracks, the whole thing works like a stencil for us. We're all familiar with stencils, right? So if I take a paint now and spray on top, if you don't disturb the system, you will have the paint enter only in the crack regions. Then I can wash away the sacrificial template. What will be left behind will be the footprint of those cracks because paint entered only there. We don't use normal paints, we use nano paints. These could be nanoparticle dispersions. Many a times, through the vacuum system, we even physically dose these metallic vapors and other active material vapors to get into those cracks, so that ultimately when we wash away the stencil part, that's also very easy. In water you can wash it away. You will end up with a fine network of these, what were originally cracks, now they are wires of the desired material. I hope you got it. This is a very important concept I'll be dealing with now. And so we deal with very tiny crack widths and thicknesses. So we have this room to fill in, and I can actually end up, we have come down to around 100 nanometer with respect to this tiny width at the bottom. So that decides the fine value of the wire, whatever you end up with. Yes. Well, we realize that a lot more can be done in crack physics. A lot many issues could be attended to. You may have seen in art museums old piece of art with lots of cracks. So if you give it to us, we'll be able to predict the age of the painting, because there are primary cracks, secondary cracks, tertiary cracks, and they take time to evolve. So we can actually almost fix the age of the painting based on the crack physics. So we have made advancement in understanding nano cracks themselves, but I'll not get into that. I'll rather stick to the main topic, that is the functional glass. So take a piece of glass and do the sacrificial coating, allow it to crack. These are spontaneously formed cracks. And then shower metal on top. In this case, we showered gold. This is a model study, okay? And so this is a fine set of cracks here. This atomic force microscopy image. You see now gold wires are left out once we dose gold on top and wash it. Rest of the gold you can recover along with the template. And so gold is left on the substrate here. These are nicely interconnected wires. If you do a bigger piece here, this 1 by 1 mm square, you can still track this wire system here, and you can see the percolation paths, plenty of them filled up. You can even map up them by using various techniques, and you can calculate also what kind of fill factor you have achieved by after putting the metal. So in this case, silver, which we have done up to 12%, that's the fill factor. We want to keep the fill factor low because we want a lot of light to pass through the glass piece. At the same time, it should be electrically conducting. So we achieve transmittance in the visible range to the tune of around 85-87%. Going forward with this, you can use this wire system, which is on a piece of glass. When I give you glass, you will not even know that it contains a mesh of nanowires. So this is a very fine mesh of nanowires. It's like mosquito mesh, but very, very fine. You will not be able to see it with naked eye. You have to push it under very high resolution microscopes. And I can use this wire system and pass a little current. When I pass the current, because it has electrical resistance, it heats up, and I can record it with IR camera, IR microscopy, and these are the actual wires here, which are sort of hot. Actually, they are quite red hot. They are hot. They are around 140 degrees centigrade or so. You can go on increasing the temperature, play with and all that. You can study the thermal property of these systems. This is just to highlight one particular fact, that there are no hot spots here. You can imagine somewhere one portion becoming very hot is not a good news for you. It has to heat up uniformly. It means that the electrical properties of this are quite uniform across the surface. And our what we make in the lab, they carry very uniform properties. Having done this, the next thing to do is to how to get in dialogue with industries. If I show a small piece of glass to Prashant, he will look at it and walk away. And maybe just share a cup of coffee and say thank you. How to scale it up? We also have to provide a lead to the industry. So we, in the lab, developed our own sort of coaters and all that. This is for the sacrificial nano mud painting. You can see such a rugged system. This took around 25,000 rupees to build up. And there's a shaker here, things like that. This one, I don't know whether it is from HHV. Yeah, something like small system for deposition and all that, whenever we do physical deposition. And this is the A4 sheet of plastic, which is coated with the tin wire. Tin, I told you, very, very inexpensive. It is 2,000 rupees per kg or something like that. And we have a couple of bars bought several years ago, and they are still in the lab. You can go on using. And this is covered with invisible mesh of tin wire. And you can achieve sheet resistance. We don't normally talk about resistance, we talk about sheet resistance. It is of the order of around anywhere between 10 to 100 ohm per square. Okay? These are tin wires. Very flexible. Now the plastic sheet is made electrically conducting. Otherwise, plastic sheet, like glass, is also electrically insulating. So the game is on. We had put one boy, just go on producing on plastic and glass, lots of these conducting meshes on top. And we want to realize now everything what is known up to electronically. Okay, we want to make a cell phone, we want to make a TV, we want to make a touch screen, we want to make electrically heated defoggers, defrosters. N number of examples we could actually reproduce in the laboratory. We even made OLEDs and all that. They're all in patents and publications. I'll not get into those details. We also thought of some new type of applications, transparent EMI shields and all that. You can see here. And gas sensors and anything transparent. Because we had the glass which is electrically conducting now, so we would replace anywhere you think of, we would replace the normal electrode with the glass. And you can see that as the transparency gets built up, it has a lot of applications. We even took it to the next level, making next generation solar cells. There also the transparent conducting electrode is required. So very many publications, very many PhDs, patents, everything emerged. But still, long way to go, long way to go. Industries come, they are extremely conservative. HHV is much, much better. But, industries come to a distance, then look at how to take the product forward. There will be, I'm not ignoring, there will be challenges on their end as well. So, but I must say that it is better to travel well than to arrive. So that has been my pleasure. Okay. So I'll just take you through one or two examples. I hope the session chair is active. I was given 45 minutes. So some 25 minutes are exhausted. Maybe I'll take another 10-15 minutes, then we can have some Q&A. So I'll take one or two, truly what we may call as technology, how you could realize. I signed up with a German company, and then we had a German university also to participate in that through the Indo-German Center. And this particular industry is known for currency printing. They print dollars and euros and whatnot. I had the opportunity to go and visit them and look at how exactly they go through the very precision printing, manufacturing, that kind of company. So somehow through the German university, Mukundan is here. So we got in touch with them and started translating our technology ideas through them. And here is the product. And this is the plastic sheet, PET sheet. And you can see here shiny bars running across, coatings. These are the aluminum coatings. You're able to see these contact pads visibly, but you're not able to see the nano mesh in between them. This is actually out of a 4-kilometer roll which was there, and this man, Marcus, he actually tore apart and said, for photograph we need it, let's go outside. So you can see it's so affordable, right? So this plastic sheet is made electrically conducting with these aluminum nano mesh here, nanowires. And the sheet resistance is down to 45 ohm per square. This company now commercialized it, and that is also available on Amazon, and they sell it in some name. It's particularly heating foil. They're selling large heating foils for internal applications. So it could see the level of the product through joint efforts. Parallelly, we also continue talking to other industries, and I'm glad HHV came forward, and we made a team, actually, technical team, involving Dr. M.G. Srinivasan and also Dr. Mohan Chandra. Unfortunately, he passed away in the middle of the project. But we had all his intellectual inputs then, and we could move forward. And Dr. Astosh and from SANS and my students, Dr. Injit and Mukesh, they also joined, and we carried out the project rather well. We also got very good rating from the review committee. The project itself involved taking a square feet of device and then bringing a metal mesh on top and compare it with, benchmark it with what is commercially available of similar properties and see where we stand. Okay, that was the project all about. And here you see the product. This is 30 by 30 square glass with the transparency to the tune of 92%, and sheet resistance down to 5 ohm per square. Okay, and if you see the graph here, what I have plotted is we can make sheet resistance the way you want it. We can even go down to 0.1 ohm per square, just that our metal wires start growing vertically high, not too high. If you make them around 500, 800 nanometer, less than a micron, they already fall into that kind of category, less than 1 ohm per square. So you can see data points here, very low sheet resistance. Y-axis actually talks about the commercial aspect, the production cost compared to the standard ITO. You can readily see that if you're talking about ordinary sheet resistances on glass, ITO coating would do. Cost-wise, it may not make much difference. But if you want to go down in terms of sheet resistance, this is where the distinction comes up. A few years ago, Samsung floated a problem statement that they're interested in 0.5 ohm per square and some 93% transmittance and all. We didn't have HHV with us those days. Okay, so we tried ourselves, but we lost because lots of these technology issues we have not addressed yet. All that I want to tell is there is global demand for such low sheet resistance coatings on glass for functional glass applications. So this is something which we achieved working with HHV. This is the, we have some water. You see the semi-pilot plant, I call it. And here we have, again, lots of know-how came from HHV. And we are not even aware of many things. So this is the glass cleaner. We working with the Bangalore industry, dialoguing through HHV, we made a glass cleaner and lots of these coating systems, spray coater, the whole view is here. And this was a technology project through DSP. And not only making these glasses, today we are making these glasses. So if anybody is interested, for you we will give free. So it is a sheet of glass we can give you with this nanomesh built on top. Just that you have to tell us for what application you are going to make use of, and having used it, you have to give us the feedback. That's all the commitment is. And we go on producing. It has the capability of producing around 10 glasses in a day. Lots of applications. As you can see, this particular transparent EMI shield, this is the glass, cutout glass, fitted into a box like this. Inside you see a smartphone screen, which is showing number 0. Number 0 is actually how effectively the EMI is able to penetrate. 0 means it is not able to penetrate. So it means it's the EMI shield. It's a Faraday cage. Just the difference is that it is transparent. So usually you have Faraday cages which are like this, completely opaque. But here is a transparent one. And you can take it forward, making through some flexible substrates and all. You can make a strain sensor out of that. So if I put a patch here, I can measure lots of signals here, on the body, physiotherapy and EEG kind of applications and all that. But it's completely transparent. And here you have another transparent touch screen here, touch pad rather, and so on. Transparent curved heater also here. So many applications we again realized after having made products working with HHV. This is one example of the known technology, that is PDLC technology, incorporating it with our type of electrodes, our type of functional glass. You can see that on the left side you have the opaque glass or translucent glass. On the right side of the application of voltage, you realize transparent glass. You can see the switching here. It's pretty fast. And this is nothing new about PDLC. In PDLC, it switches in within a fraction of a second. Just that the glass comes from our technology. So instead of buying ITO coated glasses, here they're all nanomesh containing functional glasses. Rest of the benchmarking is done. It's exactly comparable to what is commercially available. But the cost is at least 1/3 less. Well, it comes to almost 1/3 of the cost what is available in the market. And you can go on making, they are like throwaway pieces in our lab. We go on making lots of them. We can build larger structures as well. And we can control which remains transparent, which can switch to opaque and all that. And we have taken it further, trying to convert the, use these functional glasses in electrochromic smart windows. Not only that, can we make these windows work like battery? Can they store charges as well? So this has been addressed through another project. You can see here the functional glasses enclosing the electrolyte system here. And in this case, it is a porous tungsten oxide system. And with time, after application of the voltage, within a minute you can see the transparency drops here. And that is visibly seen here, right? A small piece of glass. These are charge-discharge cycles which correspond to the lithium intercalation and deintercalation. And they can stand lots of cycles, 500 cycles are shown. That talks about the stability aspect in that view graph. So these are like everyday stuff in the lab. We go on making them for various purposes. This is slightly bigger piece of glass, and by application of 2 volt, -2 volt, +2 volt, we can switch the transparency aspect. It's totally transparent. This is colored transparency. Various gradations we can try. Color gradations we can try with these devices. And again, coming to the benchmarking aspect, whatever one could be achieving through the conventional ITO coating on glass, which is the prevalent market now, one could replace it with our type of functional glass, having nanometal mesh on top of the glass. That's the functional glass aspect. While we do that, still one thing, of course it will bring down the entire process cost, manufacturing cost, presumably. I'm not a marketing guy there may be probably other hidden costs which get involved. I'm not getting into that. But one technical issue still remains around. That is the power required to keep the device in the on state. It is like you want to keep your laptop on, you want to keep the TV screen burning on. So it requires power. Similarly here, if you want the smart window to function, you need to address this power requirement. These are already quite low numbers. Okay, 4 watt per meter square is rather low, but still it requires power. So are there ways in which you can even circumvent this? This is something which went on bothering us. Can we make a glass which is as passive as today's glass, but at the same time it's functional glass but doesn't consume energy? So we started addressing this, and various ideas were tossed, and this one particular idea has clicked. It has again reached to the technology translation level wherein we are working with an industry. What it involves is take a ground glass, not ordinarily ground. We take a glass and create nano roughness there, micro nano, combination of kind of roughness. So the roughness is at different hierarchical scales now. Once we create this kind of roughness, glass tends to be quite translucent. You see that kind of glass all around, right? People even make patterns that people write names and all on glass, just rendering it to be translucent because it scatters light. Light is wanting to go in a coherent way, but this particular roughness scatters light, and because of that, you will see translucent aspect coming to the glass. What we do, as I have shown on the right side, we fill in a liquid into those roughness cavities and all, wherein they get filled up nicely. This particular liquid carries the refractive index, the optical property, exactly same as the glass. So glass suddenly feels like, or light feels like, light passing through feels like it is a slab of glass itself with no roughness. So again it starts transparent. I'm sure you have played around with these kind of toys and all in school days, but this is now at a larger scale with much better control. So you can see here the particular encased device is, you see now, it's becoming translucent on the top, and while it is transparent at the bottom, right? So we make a refractive index matched liquid flow in between the microfluidic cavities between the glasses, filling in all those nano micro cavities, but it is refractively matched, so the light doesn't feel the difference at all, so that you render the glass to be transparent. And the pictures are very clear here. So in addition to controlling the opacity and transparent aspect of the glass, we are also able to induce another property to this. That is what we call as curtain effect. It is not a defined parameter in technology world. Curtain effect is this one. Like we have half curtain drawn there. So top is translucent and bottom is transparent. And this device does not require any energy to run. If you decide to pump in and pull out the liquid manually, which you can do with a syringe, it doesn't require any energy at all. And here we have built a small motor and all because we thought we'd give some fancy switch for people to operate. Whether it is in curtain straight like this, half closed or fully open, fully closed, it is not going to consume any energy as it runs through. And that attracted the attention of industry. You can see here, power required is zero, right? With this kind of technology, it just doesn't need anything. And we talked to glass companies around the globe. Saint-Gobain is one major player in making glasses, and so they took interest. And you can now see if a technology partner gets involved, they come up with lots of ideas. So now we have an R&D project, second phase actually going on, wherein those ideas are being incorporated, and it is again at the semi-pilot level. They are developing, we are carrying out the project, giving them the feedback and whatnot. So hopefully in months to come, we will have really a product coming out of this. So this is our another aspect of the functional glass journey. And we have many more things to do. We have now the next technology project coming again from Technology Board, wherein lots of partners are involved, as you can see at the bottom. And here we want to make glass into anything, like translucent, transparent, color gradations of the desired quality. Professor B.L. Prasad is sitting here, so he also has a task to do along with his colleagues. So various those aspects are going to be put together in glass in making it into fully functional glass for window purposes, window or partition purposes. Time to thank my co-workers. You can see people who have been working with me closely. Dr. Ashutosh, Indrajit, Kritika, Rahul and Mukesh, and collaborators, lots of collaborators. So each one comes with their own knowledge bank. For example, Timothy Fisher from Purdue helped us doing the IR microscopy, and Inji Srinivasan is here from HHV, and solar cells we built in Germany with Professor Mukundan, and crack modeling we went to Professor Darafdar of Jadavpur University, and so on and so forth. This activity still goes on, but it has reached a level of maturity that I view it as a technology project, technology activity within the group. It is no longer at those basic levels. So I think with this I would sum up, and thank you all for your kind attention.
Thank you, Professor Kulkarni. We will now be having a 10 to 15 minute Q&A session.
So tea is still some time away. Suppose you can use the time in asking a few questions. Sure.
Yeah, so thank you very much, Professor Kulkarni, for your opportunity. My question is, what's the cost of your magic index match fluid that you put in between, and how is its stability?
Join us. It's available in barrels, inexpensive. It's also used in various other contexts, other industries are using. It's not one formulation. We have now at least 5 formulations working with the industry. We had only one, and so for them, what is important is whether it will be acceptable for certification. Because the agencies are very tight, right? So they look at various aspects like toxicity, flammability, whatnot. So we have gone through many formulations now, and there again, when we begin our journey, always every time we look at the cost effectiveness, extremely affordable. In terms of cost, if you compare it with the glass pen, this will be 1/5 of the price, the liquid itself.
Thank you.
And stability also is again another parameter we look at. Unless they cross 80 degrees or so, they all remain stable. Yeah, I threw away that slide on the way actually, looking at the time constraint. So if you look at the UV visible spectrum, now you have a mesh, depending on the thickness of it, it can decide how much light to transmit through the wire body itself. They're all fine wire meshes, right? So there also light can bend and pass through also to some extent, depending on the wavelength. But light transmission doesn't depend on that at all, need not depend on that. There's a very, very small fraction. Majorly light passes through in between the wires. That is why I went on talking about the fill factor. What is the footprint of this mesh? We try to retain it to be around 15% max. So in between all, you are exposing the substrate itself. Now it is a property of the substrate. If you are using glass, you cannot transmit UV. Right? So we have done a model study with quartz. We could go down to 250 nanometer and all the way to 2500 and right, you can cross that easily.
So many industries were associated with you. Did you investigate the possibility of exporting these things to other countries?
I think it's more a question to Prashant and Srinivasan. We never ourselves took up on marketing aspect. I have never done that. To the extent possible, I have gone around and participated in expos, including industry expos, and distributed pamphlets for people to take interest in our work. But we are on our own. We never did. I always coax him whether we can reach out to Amazon with the glass plate. This is actually a knowledge product. That's what I'm given to understand. So it becomes a component in another device, right? So it is not business to customer, it is a business to business model. And they are the people who are to think about do things. I hope I answered you.
It is interesting to know how the liquid is held up to the glass. Are you...
No, it's a microfluidic cavity, micro-nanofluidic cavities, network of cavities through which the fluid flows.
Okay, it is not coming out of the channels.
This is cavity in the glass.
Okay.
We had one more question at the back there.
Yeah, do you have any control over the crack pattern?
Yes, very much.
Very much.
Yeah. So the example I showed, the dried lake bed and the fine meshes water. So you can do the whole spectrum in between, different widths, length scales, and all that. There is actually good crack physics which is already established. We also contributed to some extent. So it depends on the template, whatever you're using. There is a colloidal dispersion. The particle size of those colloidal dispersions, number one. Two is whether they're hard or completely soft or semi-soft. So that also decides. And nature of the dispersing medium, liquid medium, that matters. Finally, the substrate interaction also matters. Temperature matters. So with all these parameters at play, you can optimize for any length scale you want. The lowest we have gone is crack width of around 100 nanometer.
Sir, after filling this one with nanomesh, after washing it out, what is the stability of that nanomesh with respect to the chemical stability or cleaning stability?
Again, it depends on what you have deposited. So we have worked with various metals, sulfides, oxides, and all. That goes with the parent material, what you are depositing. It's a stability in general. So if I take aluminium, it's aluminium stability.
Respect to glass adhesion.
Oh, you mean how strongly adhered to? Yeah, again, working with industry and on our own before, we have done all the adhesion tests, standard adhesion tests, and very good actually. If I give you a piece of glass coated with aluminum mesh, you'll have to struggle hard to remove it. If you use a sharp blade or something, you'll struggle. Yes, Dev.
It's not a technical question, obviously, but so you said that small gap that you wanted to bridge between the industry and then the academia, which is the toughest part that we all face, right? So,
absolutely, yeah.
How that happened? Maybe it is also a question to Prashant and then
how we
exactly right. So that small step obviously has probably made a huge difference, and I think like in a technical
with HHV we have been dealing with them, working, we are buying things from them. So I don't exactly know how the dating started, but so yeah. So
yeah,
I think it was just
As a customer, Professor and his team had visited, and then we took them through the facilities, and that's when we had completed the DST project for the large area TCO development. When they saw the machine, they felt, okay, we have a product or we have a technology with us, why don't we marry both these technologies together and make something even better? So that's how it clicked.
Absolutely. Now I have something more to add, Srinivasan. If coffee is not ready, give me 2 minutes to add this.
I think this is important.
I see some students in the audience, that's why. See, when we go out to find industry partners, strategy is very important, I feel. I have burned my fingers. I have come across people who have said, I'll write a check for you, just give me the know-how. Sign here, we are done. Okay, and my feeling is whether the industry partner has got any strategy. Here, HHV was well positioned. I'm not saying because they are here or something. This is my experience. Because they had burned their fingers. Right? The plant I was shown, the solar cell plant and all, they have gone through it. They knew what it means. This is number one. and seeing our invention, what it takes to take it forward. And third thing they came up with is, okay, let's take it through a project written with a partner. See, this shows the maturity, right? Normally you don't find it around, particularly Indian continent stuff. Either you come across big industries who are extremely conservative, they only produce, by tons and all, but they don't want to look at small players. So here is a partner who paid attention to all the details. They spent time with us. Yeah.
Sir, I'm not from science background, but I wanted to ask you something very stupid that may sound. But sir, all through the presentation, I was trying to understand what purpose this technology is going to fulfill for humanity. As in, like, we are facing so many crises, and is it right to invest so much human intelligence and finance in developing something which is not even necessary? I mean, like, we can have any sort of classes. So I know it's just like, I was wondering, like, Elon Musk is trying to colonize Mars. I was wondering, look at Earth, we have so many problems here. First save Earth, then we can go to Mars. So I was just trying to understand, and I was not able to make sense.
So it's a very valid question. By the way, I'm not planning to join Elon Musk anytime soon. Let him settle down with whatever confusion is all around. Coming to your query, this is precisely addressing the issues what you are raising now. You see, I didn't have time to touch upon. I did mention that indium is like silver, right? But one drawback with indium is, unlike silver, it is not recoverable. Silver, I have it around with me what my grandma had or her grandma had, right? It sails through the generations and we preserve these noble metals, silver, gold and all that. Indium, who cares? I don't even remember what phone I had last, I just threw it away. So it gets into the environment and in no way is recoverable. The reason is, you need not blame mankind, it's because the indium property, indium 3 plus to indium 0 is very, very expensive process. So it is not that easily recoverable, unlike silver, Ag plus to Ag 0, very easy. You got it? So there are environmental concerns with respect to throwing away ITO coated. That's why if you go to Apple's site, I'm not marketing for Apple, at least I find it on their website, they clearly talk about how they make use of each component which is coming out of the discarded phone or whatever application, right? So people are getting to be more and more conscious of the electronic garbage, the e-waste. Yeah. So in that context, our invention should play a great role, because even if you throw away a screen, you are throwing away the glass coated with aluminium. You throw away Lay chips packet as well, that is also coated with aluminium. Right? Aluminium is not such a big concern as is indium with other metals. Thank you.
So I have one question. So how about stretchability of these materials?
Well, thank you for asking that question. I showed very briefly part of one of the view graphs, strain sensor. So if you are familiar with the chemistry part of it, PDMS matrix if we use, and we can actually embed these wires into PDMS matrix. And now, as grown, it's perfect mesh in the PDMS matrix, but PDMS is stretchable. So the moment you stretch PDMS, you can see now the wires get broken, forming nanojunctions. And the beauty is, because they're all embedded, they can again come back and make contact. So you will see now millions of gaps coming up and millions of bridging back the gaps. So to one of my collaborators, I just showed, see now you are seeing 10 ohm on the meter. I will turn the strain sensor now, increase the strain. The moment you're gone, you're not even 0.5 mm stretching, the circuit opens up. And you can exactly come back in the same resistance path, back to again 1 line. Yeah. So you can do such wonderful things with this. Please, Manindra.
So I'm not an expert on this, but I just wanted to ask you: does the strain play any role? Does it give any cracks in terms of your nano mesh? And will it become a problem over the time? Because if at all we are talking about cell phones and other things, I see that as a big problem.
You are very much from the field. Why are you saying? The question what you asked is, in the first leg of the work we did this. We set up a machine wherein we have this nano mesh on the PET, and now you make the PET go on doing a bending.
That's a creep study.
And so manually we did a couple of times, few hundred times and all. Then we built a small machine and went on doing for thousands of times. So what we realized is you can see the resistance staying there. Even though it's all reported data. We have done up to 50,000 cycles of this. Okay? So it just remains there. And later on I felt a little stupid of me only, because after all, if you start with a good metal like silver or something, it will be creep resistant, right? So it will take those cycles, no issue. Yeah. Well, challenge would be if we bring in more functional like some oxide, sulfide, or even some other metals, then creep study would be extremely performant. Maybe coffee is ready, I think.
Okay. Is there any limitation on the substrate thickness? For example, you have a glass which is about 1 mm or 2 mm. Let's say I start going below that. So is there any limitation on that front?
Do you have some technology in mind?
Maybe we can discuss.
I can see that intent. No. We are not taking, there is no constraint. That's the answer. The reason being we are not taking the substrates through any, sort of thermal stress or none of those. Just remain at room temperature and plus minus 2-3 degrees, 5 degrees, that's about it. And so you can play the thickness.
All right, thank you.
Thank you again. There are no more questions. Thank you.
Thank you again to Professor Kulkarni. I now request Mr. Prashant, Mr. Nagarjun, and Ms. Leela Amazani to please present the memorial plaque to Professor Kulkarni.
Sir, ಸ್ವಲ್ಪ
I have a small impromptu note to say here. Basically, there's going to be a vote of thanks later, so this is not that. But just that on behalf of the Sackmore family, I'd like to express our sincere gratitude and thank you to the Institute of Science and especially to Instrumentation and Applied Physics Department for allowing us to build this beautiful facility here, and which we hope will really garner a lot of interest and be utilized to a large extent. Thank you.
So just before tea and coffee, I know that's on everyone's mind, I'd like to invite Professor Kaushal Varma to the dais, and I request Professor Asha to please present the bouquet and memento to Professor Varma. Thank you. I now request Professor Sai to please provide the vote of thanks.
Good evening, everyone. First and foremost, we'd like to thank Sri S.P. Narasaiah and his family for their very generous contribution for the construction of the auditorium. They have in fact contributed much more than initially committed, without which we would not have seen the auditorium in this form today. Thank you so much for the entire family. We express our deep sense of gratitude to Professor Rangarajan, Director IISc, for his kind support at every stage in all possible ways. We thank Professor Balram, former Director IISc, for seeding the thought for seeking the support from SVN Garu, which was the starting point of this auditorium. We would like to thank Professor Kaushal Verma, Dean Physical and Mathematical Sciences, Professor Anil Kumar, Dean A&F, Professor Satish, Dean P&I, for their constant support. We would like to thank Professor Fanindra Elavarthi, Chair ODA, for his kind support throughout the process. So we express our sincere thanks to all the well-wishers of the department, staff of the CCMD and administration, former and present faculty of the department, students of our department, and all the staff members. Thank you all.
One quick session before we break. Professor Shokan, on behalf of the IISc, would like to give a few mementos to some of the HHE family and people who have made it possible for this event today. So I'd first like to invite Professor Kulkarni.
Oh yeah.
Professor B.L.V. Prasad. Mr. V.K.V. Raju. Mr. Srinivasan. And Dr. Srinivasan. Mr. Prashant, Mr. Nagarjun, Mrs. Leela, Mrs. Padmaja, and Mrs. Geeta Saku.
You want us all in life?
ಸೆಂಟ್ರಿಗೆ ಬರ್ಸ್ಕೊಳ್ಳಿ, ಇಲ್ಲಿ ಬನ್ನಿ. ಸ್ವಲ್ಪ ಹಿಂದೆ ಬಂತು.
I'd also like to thank Dr. Ashokan for all the work, coordination and effort he has put in from before COVID, through COVID, going through multiple, contractors, changes, all the challenges that we faced to actually bring this auditorium to fruition. So I'd like to give Professor Ashokan a big round. So on that note, tea and coffee are ready. Thank you. Thank you.
I just wanted to thank everyone and also particularly Smriti for being with us all the time. Thank you very much.
I'd also like Ms. Bharti to come to the stage to receive a moment. Santosh and Jairaj and Prakash, if you could quickly come and get your momentum, so then everyone can take. This is the entire team that has helped put everything together today. I'd also like to invite Akram to receive a moment for the scene.
Akram. Hello, sir, you could.
Prakash spent almost 2 to 3 months here. I was telling Smriti that he is on deputation to IAC. Yeah, thank you.